Okay, so this is going to be Chapter 9, Thermochemistry and Chemical Energy. And thermochemistry is really just the physics of kinetic and potential energy applied to a chemistry-specific context. So to start off with, let's talk a little bit about some of the basic principles of energy. One of the basic ones from physics is the conservation of energy law, which is that you can't create or destroy energy. You can convert it from one form to another, but you can't have energy either vanish into nowhere or you can't create it from nothing. So a good example of converting between two types of energy is given by a hydroelectric dam. So in a dam you have water level behind the dam a lot higher than the water level after the generator in the dam. So behind the dam you have a lot of gravitational potential energy, and you can have the water flow through a generator to produce electricity, and in this process you're converting the gravitational potential energy of the water level as it falls down into kinetic energy that's used to turn a turbine that is used to produce electrical power for the electrical grid. So that's an example of conversion of energy between two different forms. The types of energy that we're mostly going to be interested in this course are thermal energy and the related concept of heat. So thermal energy is kinetic energy specifically of molecular motion, and it's basically just analogous to the temperature of an object. And heat is a related concept. It's the amount of energy transferred from one object to another as a result of a temperature difference between those two objects. So heat, basically the principle behind that is that when you have an object at a higher temperature and an object at a lower temperature and they're in contact, heat will flow from the hotter object to the cooler object until they attain the same temperature. So the first law of thermodynamics kind of formalizes the basics of the law of conservation of energy, and there's a slightly different form of this that we can use for a lot of what we're interested in. So the first law of thermodynamics says that the total internal energy of an isolated system has to remain constant. Now, we can break down systems into sort of a system and a surroundings, where the total energy change of both the system and the surroundings has to remain the same, and the surroundings is essentially all the rest of the universe outside of the system. And you can have energy, say, flow from the system to the surroundings, or from the surroundings into the system, as long as the proportionate amount of energy is lost from wherever it's flowing from, and that amount of energy, same amount of energy, will be gained by wherever it's flowing into. So if energy flows out of the system into the surroundings, delta E, the change in energy, is going to be negative because the final energy of the system is less than its initial energy. Whereas if energy flows into the system from the surroundings, our energy change will be positive because our final energy is greater than the initial energy. So if we look at a chemical reaction, and specifically the energy change associated with it, we can use the example of the combustion of methane, CH4 gas, which is the main component of natural gas. It combusts by reacting with oxygen in the air in a 1:2 molar ratio to form carbon dioxide and water, which are both gases, and it produces 802 kilojoules of energy. So remember, kilo means 1,000, so 802,000 joules of energy, essentially. And if we kind of measure the delta E associated with that, at least assuming that we're starting with a mole of methane, we're going to get negative 802 kilojoules, because that energy is released from the system into the surroundings. And a good way of thinking about this is that you're starting with chemical potential energy in the form of methane and oxygen. You get lower energy products out, carbon dioxide and water, and the energy is released into the surroundings as heat, which is why combustion reactions are associated with a heat increase. We're taking chemical potential energy and we're converting it into an equivalent amount of thermal energy. Now, Energy changes, and all the ones that we're interested in at least, are what are referred to as state functions. And this is a concept that we'll come back to a couple of times throughout this presentation because it's important for kind of helping make things work. So a state function is basically a function or a property where the value only depends on the present state or the condition of the system and not on the path used to arrive at that state. So a state function might be, for instance, the distance between two cities. So if you take a town in California and a town in Massachusetts and measure the distance between them, the absolute distance there is completely independent of what path you take between the cities. So if you take one of those paths in green, you'll take a longer distance to get between those two cities than if you'd taken just the most direct route. So the distance between those two is a state function. Non-state functions, so things that actually do depend on the path, would be things like the actual amount of distance traveled or the work expended or the amount of money that you spend, something like that. Okay, so one particular type of energy that we're going to be interested in this course is enthalpy. And the total amount of energy change of a system is based around the amount of heat energy transferred and the amount of work done. Q is used to abbreviate heat, W is used to abbreviate work. And so those are the two kinds of energy changes associated with chemical reactions. If we consider systems at constant volume, which is how most reactions behave that aren't in the gaseous phase, we can ignore the work term because that depends on the change in volume. And so the heat energy transferred just becomes equal to the delta E itself. And the QP that we're interested in there is actually the enthalpy change, which is abbreviated as delta H for some reason. And so this delta H value is actually reported in a lot of tables for specific chemical reactions. This is the amount of heat energy gained or lost in a chemical reaction. And just like regular other types of energy measurements, enthalpy is a state function, and so if you know the final and initial enthalpy values of the system and you just subtract the two of them, that gives you the enthalpy change for the reaction. And in the context of a chemical reaction, the final state is the products and the initial state is the reactants. So if we look at a couple of examples of this, these are both combustion reactions of propane, which is C3H8, which is a hydrocarbon gas. This reacts in a 1 to 5 molar ratio with oxygen gas to form carbon dioxide and water. Now, one thing that you need to pay attention to in terms of thermochemical equations, which is just chemical reactions and their associated enthalpy changes, is the actual states of matter. So we've dwelt on states of matter before because it's important for things like net ionic reactions. But if you look at the two reactions on screen here, at a glance they might look exactly the same, but the top reaction produces carbon dioxide gas and gaseous water, so essentially steam, whereas the bottom reaction has the same reactants and it produces carbon dioxide gas, but the water it produces is not in the gaseous state but in the liquid state. And if you notice, that one difference corresponds to a pretty significant enthalpy difference between those two, of almost 200 kilojoules between the two of them. And so it's important to specify states of matter when dealing with thermochemical equations, because what states of matter your products and reactants are in will change the enthalpy associated with each of them, because there's an enthalpy difference between, for instance, water in the liquid, gaseous, or indeed solid states, and the same thing is true for any other substance. So to specify how our chemical changes take place, we need to define what's called the thermodynamic standard state. And this is the most stable form of a substance at 1 atmosphere of pressure, which is basically normal atmospheric pressure, and a specified temperature, which is typically 25 degrees Celsius. That's pretty close to room temperature, at least in absolute terms. If a room was actually at 25 degrees Celsius, it would be pretty warm, but it is at least sort of within the range of room temperature. And furthermore, we assume a 1 molar concentration for anything dissolved in a solution. So that's 1 mole per liter. Another property of enthalpy that we'll come back to at several points is the fact that since enthalpy is a state function, if we essentially swap what constitutes the reactants and the products, what we're basically doing is we're transposing the initial and final states. And so we're essentially changing the order that we subtract things. And so if we take a reaction like the top reaction up there, the reaction of aluminum with iron 3 oxide, which is actually a type of reaction referred to as a thermite reaction, which produces iron metal and aluminum oxide. That is a very exothermic reaction, and if you've ever seen a video of a thermite reaction, you're probably aware of the fact that that is a very energetic reaction. It releases a lot of heat, to the point where in this equation here it shows iron as solid, but really the iron produced in thermite reactions is often, at least initially, in the liquid state, because the heat of the reaction is so high that it actually melts the iron. And when we write it this way, the reaction has an enthalpy change of negative 852 kilojoules. If we were to transpose the reactants and products there, so we take that top equation and we take the reactant side and move that over to the product side, and the initial product side and move that over to the reactant side, we have a chemical equation that's exactly the reverse of the previous one. And because of the fact that enthalpy is a state function, transposing these and therefore sort of reversing the order that you subtract the initial and final enthalpy states, you end up with an enthalpy change for the reverse reaction that is exactly the same magnitude but with the opposite sign. So the initial reaction had an enthalpy change of negative 852 kilojoules. The bottom reaction, its reverse, has an enthalpy change of 852 kilojoules as well, but it's positive instead of negative. And there are specific terms that refer to reactions that have negative enthalpy changes versus reactions that have positive enthalpy changes. So specifically, negative enthalpy changes are associated with exothermic reactions, and positive enthalpy changes are associated with endothermic reactions. So next, in terms of enthalpy, I want to look at a few specific types of enthalpy that are associated with changes in states of matter. So I've mentioned previously that there are 3 basic states of matter, which are solid, liquid, and gas. And for any given substance, there's a certain amount of energy change associated with transitioning from one of those states to the other. So the enthalpy of fusion is the amount of heat necessary to melt a substance without changing its temperature. And melt here refers to probably how you conceptualize it before you ever set foot in this class, which is to say that you're starting with a solid and you are converting it into a liquid. Ice cubes melting, you're starting with solid water, which is what ice is, and converting it into liquid water. So enthalpy of fusion is the amount of heat associated with taking a solid and turning it into a liquid without actually changing its temperature. So this happens at the melting point of that substance. The enthalpy of vaporization, as the name kind of implies, is the amount of heat required to vaporize a substance, and that refers to taking a solid in its liquid state and converting it into a gas. In the context of water, this would be taking liquid water and boiling it to turn it into steam, which is the gaseous form of water. And finally, there's an enthalpy change with a process that you may not be familiar with outside of this class, which is the enthalpy of sublimation. And sublimation refers to the amount of heat required to convert a substance from a solid directly to a gas without going through a liquid phase. So in everyday terms, this might be a little bit difficult to conceptualize. However, if you've ever played with dry ice, you might be familiar with this phenomenon. So dry ice is the solid form of carbon dioxide. You can actually buy it at the grocery store. And the point at which carbon dioxide goes from being a solid to being a gas is about negative 78 degrees Celsius, or I believe it's a little bit below negative 100 degrees Fahrenheit, so it's very cold. But at that temperature, your pellets of dry ice, as they heat up, will actually transition from being a solid to just evaporating without ever melting. And so the pellets just kind of slowly shrink and disappear as the carbon dioxide escapes as gas, and there's never any liquid state in that process, at least not under normal atmospheric pressure. And in the context of water, since that's kind of the most ubiquitous substance and the one that you're probably most familiar with the different phases of outside of this class, we can make a potential energy diagram showing all of these phase changes. So from solid to liquid is enthalpy of fusion, from liquid to vapor is the enthalpy of vaporization, and from solid directly to vapor, which is possible for water under certain circumstances, usually under low pressure, that corresponds to an energy change that is the enthalpy of sublimation. Now, a few things to notice about this potential energy diagram. The higher you go in this diagram, the higher the energy. So the amount of energy required to go from the solid to the liquid state, that enthalpy change is positive because your solid ice needs to absorb energy to convert from the solid into the liquid phase. Likewise, if you go up in this chart from liquid to vapor phase, or the gaseous phase, same thing, that enthalpy of vaporization is going to be positive because you need to put energy into the liquid to essentially break apart the attraction of the molecules between the other water molecules to separate them out into the gas phase. Another thing to notice here, besides the fact that sublimation is also a process with a positive enthalpy change, is the fact that because enthalpy is a state function again, the enthalpy of sublimation is the same as the enthalpy of fusion and the enthalpy of vaporization added together, because the total amount of energy change in going from solid to liquid and then liquid to vapor is the same as going directly from solid to vapor, because our starting and ending points are the same in both cases, even if you take a different path when you go from solid to liquid and then to vapor. Also, because of the properties of enthalpy change, if you go in any of the opposite directions, so say from vapor to liquid, or liquid to solid, or vapor to solid, all of those processes have the same enthalpy change as the enthalpy changes that you see on this diagram, but the values are negative.